Hi students, this is going to be the second video lecture for the subject EC304 VLSI. In this lecture we will learn Module 4, MOSFET Logic Design. The contents to be covered in this module are the pass transistor logic, complementary pass transistor logic, transmission gate logic, and the realization of functions using the above logics. We have already learned how to realize a digital logic function using CMOS inverter or CMOS logic, and that is categorized as gate logic or restored logic, where the basic building block of a logic function realization is an inverter circuit, and the inverter circuit that we have learned in last module is CMOS inverter. So in this module, we will learn how to realize digital logic functions using switch logic, where the basic building block is pass transistor and transmission gates. Pass transistor simply represents N switch, P switch and C switch, and this is commonly categorized pass transistor logic. Moving on to the core content of this module, that is the pass transistor logic. I have already said that pass transistor logic mainly comprises of N switch and P switch, which is nothing but our NMOS and PMOS transistor. Hope you remember the symbol for an NMOS transistor. It is shown in the slide. You can see here we have the input terminal, output terminal, which is nothing but the source terminal and the drain terminal, and we have the control terminal, that is the gate terminal. The pass transistors are commonly used for logic realization for the easiness, because it requires less number of transistors to realize the various digital functions. So hence pass transistors are widely used in the design of ROM, PLAs, multiplexers, etc., and we will learn how to realize it. Moving on to the working of N switch. You can see here N switch comprises of the source, drain with the gate. We all know N switch is having a positive threshold voltage. So whenever a gate is applied with a positive threshold voltage, the switch will get closed. So you can see here, when here G is equal to 0, the switch is open, and when G equal to 1, switch is closed. So when switch is closed, as we give source terminal a zero logic, it will be passed to the 0. It will pass 0 as to its output. Now in case of here, as we give 1 as input to the source terminal, the output drain terminal receives that 1, but it is not actually the one that we have already given here. It is actually a degraded one, or poor one, or weak one. We will learn about these concepts in the later slides. First we will learn why the first case, that is when Vg equal to 0, what happens, why the switch is open. When Vg equal to 0 and Vs is equal to 0 or 5 volt, you can see here what is VGS. VGS is nothing but Vg minus Vs. So 0 minus 0 or 0 minus 5. So it is actually 0 or a negative voltage, which is less than our positive threshold voltage for the N switch. That's why the this N switch is always open for this case. So the output for this case is always 0 or at high impedance state. Next, before moving on to the next working of N switch, we should learn the definition for strong and weak logics. You can see here, strong one is defined as a voltage range between 4.5 to 5 volt, and weak one is defined as a voltage between 3.5 to 4.5 volt. Okay, so any voltage which is coming in between 3.5 to 5 will be considered as 1, with a special category for strong one and weak one. Now you can see here, what is strong 0? Strong 0 is actually the voltage range between 0 and 0.5 volt, and weak 0 is the voltage that is just above the 0.5 voltage range, that is 0.5 to 1.5 volt. So with this knowledge we can move on to the next slide. Why N switch seems to pass strong 0 and weak 1? So you should understand this sentence, because in university always they ask to justify why N switch seems to pass strong 0 and weak 1. Case, so we are actually considering three cases under Vg equal to 1 or 5 volt case. Then only we should be able to justify this statement. So case 1 is that consider Vg equal to 5 volt and Vs is equal to 0. So 0 represents here strong 0. Say voltage, we are going to apply voltage range between 0 and 0.5 volt. So when we apply Vg equal to 5 volt means we are applying a logic 1, and Vs is equal to 0 means we are applying a logic 0. So what is going to be the output? That is what we are going to analyze here. What is the value of VGS? VGS, how we calculate VGS? VGS is nothing but Vg minus Vs. So that is actually 5 minus 0. So 5 volt, which is greater than our positive threshold voltage. So we are assuming a positive threshold voltage for the NMOS transistors 1.5 volt. 5 volt is greater than 1.5 volt. So the switch gets closed and we will obtain the output as, so the input is passed to the output. That is why the term pass transistor. Okay, the output is equal to input, which is here our strong 0. Next, case 2, consider Vg equal to 5 volt and Vs is equal to 5 volt. Here 5 volt, so what we are actually applying? We are applying to the gate terminal a logic 1 and to the source terminal another logic 1. So Vg equal to 5 volt, Vs is equal to 5 volt. So what will be the output? Again, the same procedure. Calculate VGS. What is VGS? Vg minus Vs. That so 5 minus 5, 0 volt, which is actually less than VTH. So what is our VTH? Plus 1.5 volt. So 0 is less than 1.5 volt. So what happens? The switch will not open, because for N switch to get turned on, the threshold, minimum threshold voltage should be plus 1.5 volt. So the N switch will not get closed. So that's why N switch does not passes strong 1. Okay. Next, consider the third case. Consider Vg equal to 5 volt and Vs is equal to 3.5 volt. Remember the weak 1 range. This is the voltage which is coming under weak 1 range. So what is VGS here? VGS is equal to 5 minus 3.5 volt, which is equal to 1.5 volt. So it is actually the minimum threshold that is needed to turn on the NMOS transistor. So in this case the switch will get closed and the input will get passed to the output. So the output is equal to weak, is equal to 1, which is actually equal to weak 1. So from these discussions you will consider, you will think what will be the case for a weak 0. We can actually imagine for weak 0, consider same situation by replay Vg equal to 5 volt, and instead of Vs you can consider any weak 0 voltage, that let's assume 1.5 volt. So 5 minus 1.5 volt is actually 3.5 volt. So 3.5 volt is actually greater than VTH, and for that case also the switch will get closed. So we can conclude that for N switch, N switch will pass both strong 0, weak 0. Need not to specify. So we can say N switch passes 0, logic 0, as well as logic 1 in a degraded format. Degraded format means it passes only weak 1. So you can see here a summary of the working of N switch. 0, 0 will pass, or as the gate or gate logic is 0, it will not pass. The output is at high impedance state, because for logic 0 gate will not get turn on and the switch will not get closed. For gate equal to 1, logic 1, the switch will get closed only for what? Only for logic 0, and we will get the output 0. For logic 1, when for input voltage 1 at the input terminal, for logic 1 at the input terminal, it will pass to the output, but that output will be a degraded one. That is the core key point that we need to understand in this session. Moving on to the next, that is the working of P switch. So as we have discussed the working of N switch, P switch is also having 3 cases, and the working of P switch is just the complement of N switch. You can see here, this is the symbol for a P switch, source drain terminal with the gate terminal. You can see here bubble distinguishes P switch and N switch. P switch will be having a bubble, and this P switch is having a negative threshold voltage. So here, as we apply a gate voltage equal to 1, what happens? It will not get turned on. The switch will not get closed. And as we apply Vg equal to 0, that means we apply so that the gate source voltage then becomes negative and the switch will get closed. So for negative voltages, P switch will get closed, and for positive voltages, the switch will be open. And the common conclusion that we are going to derive in this case is P switch will pass a strong 1 and a weak 0. So consider Vg equal to 5 volt and Vs is equal to 0 or 5 volt. So what is Vgs here? This is the case for G equal to 1. Okay. Why the switch is open for this case, that we will first analyze. When Vg equal to 1 or logic 1 means Vg equal to 5 volt, and S is equal to 0 means Vs is equal to 0 or 5 volt. We can give anything, because for Vg equal to 5 volt, Vgs becomes 5 minus 0, that is 5, or 5 minus 5, 0 volt. Hence always what happens? We need a negative threshold voltage. So here the output will always remains in 0 or in high impedance state. So switch is open always when Vg equal to 1 or at 5 volt. Next, moving on to our 3-case situation. Why P switch seems to pass strong 1 and weak 0? So this is the sentence that we need to justify. So consider case 1. Case 1. Consider Vg equal to 0 volt and Vs is equal to 5 volt, or which is otherwise known as strong 1. So what is Vgs here? So Vgs, so same steps are following in here also. Calculation of Vgs and see what is its Vgs voltage, and we need to check whether the Vgs voltage is attaining its threshold voltage or not. What is the value of Vgs? Vgs is 0 minus 5, that is minus 5 volt. So minus 5 volt, when we compare, if we assume the threshold voltage of PMOS transistor is minus 1.5 volt, so it is actually more negative than the actual threshold voltage. So the switch will get closed, and hence P switch will pass its input to its output, and here the input is the strong one. So that's why it says that P switch passes strong one. It's actually it's by mistake. Here Vs should be 1.5 volt. Okay, okay, and the 1.5 volt is actually coming under weak 0. So when I will share the slide, I will make the change. For the time being, consider Vs as 1.5 volt, which is considered to be weak 0. Okay, so here it is written, input is 1.5 volt or weak 0. So what is the value of Vgs? Vgs is Vg minus Vs, that is 0 minus 1.5, which is equal to minus 1.45 volt, and this, which is nothing but our threshold voltage for the PMOS transistor. So our P switch will get closed for this condition, and it will pass the input to the output, and the input logic for this condition, this case, is weak 0. So we will get weak 0 as the output. So as a summary, we can say P switch passes strong 1 and weak 0, whereas N switch passes strong 0 and weak 1. You should understand this concept clearly, because it will surely ask for the university exam to justify the statement why P switch seems to pass strong 1 and weak 0, or N switch seems to pass strong 0 and weak 1. So, and you need to explain this point by clearly stating the three cases. Moving on to the combinational logic using N switch and P switch. So consider two N switches in series connection. So you can see two N switches in series connection. So as we apply 0, 0 to these two switches, what happens? N switch will not get turned on, because for an N switch it has got a positive threshold voltage. Or just remember, for NMOS is equal to 1, it will get turned on. For PMOS equal to 0, it will get turned on. For this case, we need to bother about only N switch. So 0, 0, it will get turned on. 0, 1, this switch will get open and this switch will get closed. This will go on, this will off, this will on, and this will off. So this is the output is. So for this case is all, the output is off, because for the input to pass from A to B, the entire path has to get closed, and that condition is only for this one. So this realization is nothing but the AND gate realization. So when two N switches are connected in series, we are obtaining the AND realization. Hope you remember our logic realization using CMOS inverter. There we have, there I have explained when we realize the logic function under complement, we are actually realizing the NMOS transistor part or pull down part of the CMOS inverter. There we need to connect for AND function, we need to connect the switches in series fashion, and for plus for OR function, we need to connect the switches in parallel. So this has actually derived from these conclusions. Okay. Moving on to the next, where the two P switches in series connection. I have said the P switch will get turned on when we apply logic 0. So here you can see for the first condition 0, 0, this gate will turn on. For the other cases, what happens? It will all are off. So this connection is actually representing NOR gate realization. Next comes two N switches in parallel connection. When we connect two switches in parallel connection, you can see only for the first condition the input is not connected to output. For all other rest of the conditions, either one of the path is connected to A and B, and for the last condition, both the paths are connected to from input to output. So this actually realizes the OR gate. Now what happens when two P switches in parallel combination? So using the when two switches in parallel combination, we are actually realizing the NAND gate function. So with this combinational logic, basic combinational logic realization, we can realize any logic functions. In your university exam, they will be giving a digital logic function to realize, and we need to realize with these basic principles. Let's see how to realize an XOR function. What is an XOR function actually? A B complement plus A complement B. You need not bother about it, you need not think about anything. You only focus on these logic functions. What you can see, A into B complement. So A into B. Here is an AND function is there. So to realize an AND function, what we need to do? We need to connect the two inputs in the series function. Here also A complement B in two series connection, and these two terms need to be together or wired using a parallel combination. And at the top we need to give VDD, and from the bottom we can take V out. So this is the realization using XOR realization using the NMOS pass transistor. Similarly, you can realize the XNOR realization. Only you need to know the logic function for XNOR function. XNOR, that is AB plus A complement B complement, and AB in series, A complement B complement series, and both these two functions in parallel. Next is 2:1 mux using pass transistor logic. So hope remember, mux is many input single output logic or function. So here we have two inputs D0 and D1 and one select line. Depending upon the select line value, it will pass the input to the output. If the select line remains logic 0, it will pass D0, and if the select line remains 1, it will pass D1. So the expression for 2:1 mux is y equal to D0 S0 bar plus D1 S0. So you can see this is the pass transistor logic realization of a 2:1 mux. So here it is simply D0 S0 bar, that is actually shown here, D0 S0 bar, and here is D1 S0 is the other term, so D1 S0. So you will finally realizing. So this is actually the pass transistor. This is when we wired these two using parallelly. If we wired these two functions, then we can realize the mux. Next comes the 4:1 mux using pass transistor logic. So here four inputs are there and two select lines. So first step is to write the logic function for this 4:1 mux. Then this is the logic function. Y is equal to D0 S0 bar S1 bar plus D1 S0 bar S1 plus D2 S0 S1 bar plus D3 S0 S1. So D0 will only be selected if both these two transistors will get turned on. For these two transistors will be turned on only when S0 and S1 is equal to 0, 0. Because S0 bar and S1 bar will be then 1, 1. So these two pass transistors, these two N switches will get turned on for that, and we will get D0 Y equal to D0. Similarly for all other inputs cases. Next comes, till now we have learned the basic pass transistor logic. Next comes another pass transistor logic known as complementary pass transistor logic or differential pass transistor logic. So the basic building block for a differential PPL or CPL is NMOS or CMOS transistor itself. So in the following slides we will use the NMOS transistor to define a DPL or CPL. So a CPL will accept both true and complementary inputs, and it will output both true and complementary outputs. That is a specialty of complementary pass transistor. Was that A, B, A complement, B complement. Here also A, B, A complement, B complement, but in previous case here it was at this point here we have B and here we have B complement. For OR and NOR case we need to just simply switch the position of B complement and B. Then you will get F equal to A plus B and F bar equal to A plus B all bar, that is OR function and NOR function. Next is the realization of XOR and XSTAR using complementary pass transistor logic. Here also we are using the same configuration structure. We are using 4 transistors only for NMOS transistor. Here you can see we are using the input as A complement, A complement A. Okay, you need to understand this as A. And if we give control signal as B complement B, finally you can try, we will get F is equal to A XOR B and F complement as A XOR B all complement, which is nothing but XOR and XNOR functions. So that's the logic function realization using complementary pass transistor logic. Now regarding the features of complementary pass transistor logic, you have noted one basic advantage, that is the configuration used to design any logic function, AND, NAND, OR, NOR, XOR, XNOR, all are same, only it uses F or N switches. Only difference is in the position of input and the control signals. So if we wisely give the input signals and the control signals, we can realize any function, and that is the beauty of CPL. The design is that's why it is said, the second point said, the design is very modular and regular, as all the gates are exactly use the same topology. Also, it can realize complex gates such as XOR and ADDers can be realized efficiently with a small number of transistors. In C-switch, there exists no degradation of output logic function occurs. The disadvantage of N-switch, P-switch, and that is pass transistor logic, N-switch, P-switch, and the complementary pass transistor logic was that they got a degraded output. Okay, so the outputs at the output logic levels will be a degraded one. As we have already said, N-switch will pass only weak 1 and P-switch will pass only weak 0. So that disadvantage is actually rectified at the transmission gate logic, where there exists no degradation of output logic. But during fabrication, as a transmission gate is made of two transistors, that is N and P switch, more area is occupied, and two complementary signals, that is VG and complement VG, is needed to drive it. So it is also called double rail switch. Double rail switch. Actually, C-switch is nothing but our CMOS logic itself. That is, for CMOS logic, what is the building block? Basic building block, CMOS inverter. And I hope you remember the structure of CMOS inverter. CMOS inverter is made of a PMOS transistor and NMOS transistor with both the source terminals connected to there and both the drain terminals are okay. As good 0 and good 1. Working of C-switch. C-switch passes strong 1. You can see here. When G equal to 1 or 5 volt, G bar is equal to 0 or 0 volt. What is here? What is VGS? VGS is equal to 5 minus 5, 0. So what happens? N switch will not get turned on. And what is here? 0 minus 5 minus 5 volts. So P switch will get turned on and it will pass VG equal to or pass the strong one. Next case, C switch passes strong 0. Why it said C switch passes strong 0? You can see when VG is for here, VG equal to 1 or 5 volt and VG bar equal to 0 or 5 volt and S is equal to 0 or 5 volt. We are using this, we are analyzing strong 0 case. So what is VGS here? VGS for the top path, it is 5 minus 0, so 5 volt. So it is enough to turn on the N switch, and here 0 minus 0, so 0 volt is not enough to turn on the P switch, so it will be open. So output is equal to strong 0. Now next few slides represents the logic realization using the transmission gate. Two input XOR using transmission gate. For any logic realization, students, please remember, only you need to know the logic function. Just write the logic equation realizing that function. So what is the logic function for XOR input XOR gate? A dot B bar plus A bar dot B. We need to, so when we are going to realize a logic function using XOR gate, draw the symbol as such. With you can use here with top represents, you can either represent the NMOS transistor at the top or PMOS transistor at the top. In the coming slides I have used this configuration, that is PMOS is at the top and NMOS is at the bottom. And just remember to realize this function A dot B bar, A dot B bar. Okay, the bottom N switch will see, N switch will actually going to realize the N switch. So A dot B bar plus A bar dot B. So when we are putting A bar here, just give the opposite function as the gate input to the PMOS terminal. When we are using, here you can see, here we have given A as the control signal, its complement A bar should be given as the gate terminal for the PMOS transistor. Here we have A bar is given, its opposite A is given as the PMOS control signal. Okay, then finally you are actually getting, you realizing A XOR B. So you can check if A equal to 1, what happens? If A equal to 1, then F is equal to B bar, and when A equal to 0, then it will pass F is equal to B. Okay, so if you do write the truth table and if you apply all the input corresponding, you can see this is nothing but F is equal to A XOR B. Next is 2 input XNOR using transmission gate. What is the logic function for XNOR gate? A dot B plus A bar dot B bar. So again same principle, same logic. A into B plus A bar into B bar. If we have given A here, what should be the control signal? Here it should be A bar. If we have given A bar, what should be the control signal? It should be here A. So finally you will get it as A XOR B or complement. Next is the realization using 2:1 mux realization using transmission gate. Here also the same formality. Do write the logic function. So D0 X0 bar plus D1 X0. So D0 X0 bar plus D1 S0. So if we have given S0 here, S0 bar here, the top signal should be S0. If we have given S0 here, the signal should be S0 bar here. And its parallel function you realize nothing but this function itself. Now how we can realize a 4:1 mux realization using transmission gate? It will be looking like this. First you should write the function and then you try to realize this function, the expression. So the first part you can see D0 S0 bar S1 bar. So D0 S0 bar S1 bar. Sorry, I have missed one bubble here. You actually need to put a bubble here also. So if you have put S0 bar here, what should be the top signal? S0. If you have put S1 bar here, the top signal should be S1. Similarly for all other input cases, and which is Y is nothing but this logic realization itself. So the total number of transmission gates that we have used in this realization is actually 8. And for each transmission gate, the number of transistors is actually 2. So 2 into 8, the total number of transistors used for this circuit realization is actually 16 transistors. We have seen what we have all seen. We have seen the pass transistor logic. We have seen the working of N switch. We have seen the working of P switch. How to various combination logics using this N switch and P switch, and we have realized some functions. Then we have seen the complementary pass transistor logic or differential pass transistor logic, which is again making use of N switch or P switch. So the disadvantage of all these pass transistors is that it outputs a degraded logic level. So to overcome that disadvantage, we have gone for the third logic, that is a transmission gate or C switch, which is actually a combination of P switch and N switch. Sorry to say that I have previously said it is nothing but CMOS inverter itself. It is actually wrong. It is not a CMOS inverter or CMOS logic. Transmission gate is another type of logic. Okay, and we have seen its the various function realization using transmission gate also. So with that, module 4 is almost complete. I will post one more video regarding the analysis of the N switch and P switch circuits, its output characteristics. We need to study that topic also in module 4. Thank you all. Stay safe. Okay, thank you.